Okay, welcome back, everyone. It's great to see you all. So this is week 2 of our course. We will talk, and unfortunately, this is a short week due to the holiday, the Independence Day on Saturday, which is observed on Friday. So we'll have everything reduced by 1 day, so we have to cut the lecture material. But in no way I want to sort of rush through it. So if something will not be understood, or something won't have time to cover something, I'd rather move it to the next week. Or anyways, we are pretty flexible on choice of topics, if you want to say. So it is okay if you want to cover by the end of the class, maybe some chapter, but like we'll definitely cover some, the core syllabus in the course. So today and tomorrow we'll lecture, well, in our style. So I'll be asking you questions. It will be more like sort of lecture / discussion style. On Wednesday we'll have the quiz, which will happen. So for most of you who have your sort of the let's write it down. So we have two sections here. So one of you are scheduled to have a lecture from 10 to 12. So the quiz will be, so quiz for 10 a.m. class will be at 11. 11 a.m. Let's do 11 then. Let's stick with Berkeley time, right? So 11:10 a.m. Right. So it will last for 50 minutes, and so it's a take-home quiz. So the way it's going to work, I'll upload the PDF file as an assignment, which will be called quiz 1. So you need to download it to your device and then start working on the quiz at 11:10. Then between 11:10 and 12 a.m. Right, since you have to still upload the materials, you will be given time to send it to upload it back. So and then upload it on B courses by 12:15 p.m. The extra 15 minutes, if you want, you can take this extra minutes to solving problems if you don't need that much time for uploads. For example, if you have a tablet, right, so and you sort of write on top of it. So the way I'm going to make the problems, I will like write the problem and then leave like the page full of empty space where you can annotate. But either way, it's fine. You can write on your paper, then take pictures of the paper and upload your solutions to B courses. So it's better to upload them on B courses than to send them to me via email, because, well, I mean, that's how the graders, that's how the GSIs will be grading them. Like you do use the B courses software for that. Okay, so that's the quiz for the class at 10 a.m. and then quiz for the 11 a.m. class. So, like I said, so if you can, if you think you want to take it at 11:10 a.m., then you're welcome to do so. But for you especially, the class, the quiz will be at 1 hour later, right? So it will be at 12:10 a.m. So it's 12:10 to 1 p.m. right? And then upload solutions by 1:15 p.m. Okay. Yeah, and then before that, so before 11, we'll have some Q&A session. So it will be like a discussion. You can ask me questions. It will be like another office hours. So maybe I should put it here. So Wednesday, 10 through 11, we'll do office hours. Hour, should I say? Okay, does it sound good? Any questions about that? I will send like a detailed instruction. I'll make an announcement on these courses. Yeah, right. So those of you who have DSP letters, I will approach you individually. So if you need some special arrangements, so you will be you can please contact me via email. Well, today, tomorrow, and we'll arrange the quiz for you. Correct, right? So some of you need more time, some of you have other restrictions. But if everything is fine and then you are assigned to any of those sections, so the quiz will be for 1 hour during one of those sections. So Shaila, did the confusion, was it resolved or still? Any other questions? Not really. Okay. Yeah.
You have 12:10 a.m. Like, are you?
We have two sections, right? We have one section at 10, one section at 12. So the quiz lasts for 1 hour. Yeah. So I want to make it available for those who are assigned to the 12 a.m. Oh, sorry, p.m. That's what they're confused about.
Okay.
Okay, sorry. Yes, good point.
Okay.
Yeah, so because some of you have like it for 13 hours. No.
Okay.
Yes, on Wednesday. The quiz is on Wednesday. So perhaps I should move Thursday from here. So it's all about Wednesday, and then Thursday we'll have a discussion on the material of week 2. Discussion on on vectors and 3D spaces. Can we take the quiz with the other section? Yes, you are welcome to take. Okay. So I need to figure out how to upload the. Okay. So what's this? Yeah. So Shinpei, can you send me a message? Right. So can you send me a message that you want to take quiz with another section? Because the way I'm going to do it on B courses, there's a way to share some documents only with certain students. So I'm going to share the quiz with the first group at 11, and then at 12 I'll share it with the rest of you. So yeah, so if you want to do something like that, please send. I think I just send you an email separately. So yeah, so if you have a DSP accommodation letter, you will get a separate quiz, or if you have some other circumstances. Okay. Emma was asking, what's the syllabus for the quiz? Well, the quiz will be covering the material of week 1. Quiz. So it's a section 10 of the book. It's a quiz on the material of week 1. Yes, Ananya, that is correct. Yes, I will do that. But you said earlier we could take the quiz. So if you want to do that, yes. So like I explained to Shinpei, so if you want to do that, you need to notify me. So if you think you're going to take the quiz with the other section, send me a message and I'll just email you the quiz separately. Yeah. I hope there won't be too many exceptions. If there will be something, it will be too complicated logistically. For the next week, we'll figure out some different schedule. Of course, I mean, ideally it would be easier just to have everybody have the quiz at the same time, but other folks may have classes at the time, so we can. Will it be proofs on the quiz? No. So think of a quiz as the problem at the same level of difficulty as the homework problem. There is no lecture on Monday. Which Monday? Today is Monday, we're having a lecture. You mean next Monday? Oh, Wednesday. Yeah. So the first class, good. So at 10 we'll have discussion / Q&A. So I can answer questions. We can look at some problems. For the first hour, we'll have a discussion. Then once that is done, I'll let you do the quiz. Let's see, did I answer everything? Okay, good. Will the quiz be based on the homework? Yes, the quiz will be based on the homework of the first week. I mean, yeah. So what I think the correct statement says that the level of the difficulty is the same as the homework. Yeah. Okay. Well, I hope things will go smoothly, right? So it's but sort of please don't panic. Like, don't be if something like there will be some technical issue, like you won't be able to log in online at the given time or anything like that. So let me know. We'll sort it out. I understand that some of you are in different time zones, so I cannot. So yeah, or let's say if you cannot make the quiz due to some. Well, I mean, if you're here right now, I guess you can make it, but I'll send a message. Like maybe some of you who are in different time zone, he or she cannot do it. So we'll do the arrangement for them especially. Okay, good. Yeah. So there's a couple of more announcements. I think some of you get confused about the status of the homework. So we don't collect, neither we collect it nor we grade it. So think of the homework as the sort of exercise, and so the reason why we give it to you is that when the book is big, and then we want to focus on certain aspects of the material which we think are most relevant for the course. So that's why the homework is what it is. You of course are welcome to, if you have time and if you want to do it, you can solve other problems from the book or from anywhere else. But sort of the homework is the bare minimum that you should be able you need to do. Can we check our answers on homework? Yeah. So I don't have the keys in my materials, but as I said in the beginning, you can just always ask the computer how to do it. So unless most of the problems are simply computational and it's easy to verify, let's say you want to plot something or you want to calculate the volume or calculate the length of the curve. If you have any problems with the question, like if you don't know how to solve a problem, you're welcome to bring it during office hours. Right. Okay. Yeah. So otherwise, all the materials are on B courses. I just uploaded the full iPad notes from week 1. Our discussion on Friday, almost 3.5 hours of it is also on B courses. Like there's a link in Zoom, and also in folder files, I saved the whiteboards from Zoom. So not only in the video, but also in the notes. Okay, I think we should continue with our material. So if there are any more questions, we'll can sort them out later. Okay, so let's talk about three-dimensional space. Well, what last week we discussed two-dimensional space, and then we can think of a two-dimensional space as a set of points which are parameterized, by a pair of real numbers. And so if you have this x and y, you can see I'm drawing the xy plane horizontally. Well, you'll see why. And now to go to 3 dimensions, we just need to add one more axis. Right, so this is, it's called z-axis, and then a point in 3 dimensions, therefore, is given by 3 numbers, x, y, and z. In that order, so order does matter, right? So there's the first coordinate, second coordinate, and third coordinate. So that and you can draw them you can think of this as a point in 3 dimensions where x, y, and z are locations that they are the following things, right? So you can you can draw the perpendicular line from that point to z-axis. That will be its z coordinate. You can do the same. You can now do the same with all the others, right? So this will be x, and this will be y. So in particular, if you forget about the last coordinate, right? So I just say forget z. What will happen if you forget z? Well, in particular, let's say we don't just forget it, but we say we put z equals 0, right? So then we have x, y, and 0, and that gives us the two-dimensional. So that will give us the two-dimensional plane over here, which lies at position z equals 0, right? So, oops. So this entire plane, the xy plane, it's a plane which is characterized by equation z equals 0. And so one condition, z equals 0 in 3 dimensions, it cuts you out the bottom, right? It's not the bottom, it cuts you out the z equals 0 plane. Well, let's see what else can we forget, right? So of course you can see here that if you have, let me write the coordinates a bit differently. So well, let's do it like this. We have x, y, and z. Those are 3 numbers. Again, order is very important. We'll explain why later. So we can forget z. We can put z equals 0. That will give us xy plane. We can forget y. Put y equals to 0. That will give us xz plane. Where is xz plane? It's the plane when y is equal to 0. So it's this plane. And finally, you can forget x, put x equals to 0, and that will be the yz plane. On the back, this is the yz plane. Right, so, and then, yeah, let's just draw it for completeness, the xy plane on the bottom. And all these planes, they intersect at point 0, 0, 0, which is the origin of the three-dimensional coordinate system. Of course, I mean, we'll know how this looks like if you are in a room, you know, without some fancy architecture. whenever the two walls and floor meet, you get exactly this this configuration. So this way you can see here that xy and yz plane, they intersect over the y-axis. XY and XZ plane intersect over x-axis, and XZ and YZ plane they intersect over z-axis. Basically, if you have the same letter in these two planes, if you look at the intersection, they will intersect over a line. And of course, all three planes they have a common point 0, 0, 0, which is the origin of coordinates. Okay. Right. So let's do assignments of points. But let's talk a bit more a bit more detail about the coordinates. So, oops. We'll do it like that, right? So, notice that I said a couple of times that order of these two numbers matters. So the way I do it, I write it x, y, and z, such that, so if you look at my video, such that they are oriented. If you take the first three fingers in your right hand, right, it's important that you're doing right hand, and then your thumb goes along the x-axis, your index finger goes along the y-axis, and the middle finger goes along the z-axis. So, and that's why you have 1, 2, and 3, x, y, and z. If you do that the same thing with the left hand, tilting. So you're tilting the axis. That refers to what? The left hand or to what? So tilting when you change an angle, right? I'm not. So they still meet at straight angles. I understand tilting. Okay. So yeah. So this is called right. Well, right triple of x, y, and z. Okay, so and then the left triple would be, so this is also a right triple. Maybe I can do smaller picture because we won't really be using the left one. So if this is x, y, and z, and you can do this exercise with the right hand. So vertical, yeah. So it's up. So Christian, it's up to you. So you can, like I said, so take your right hand, and then, well, if you do it like this, then z will be vertical axis. But if you do it like that, it's whatever it goes, right? I mean, we live in three-dimensional space. We don't have any. So assume there's no, there are no objects, like you're in empty space, like you're flying somewhere in empty space. Then of course there are no reference points. So it's up to you how you pick your coordinates. So when you just say, okay, I pick z-axis there, and for me it's up, whatever that means. So of course, when you live on Earth, right, there is a definitive direction of down, and then it's convenient to pick it up, right? That's sort of to select z to be the axis that goes up. But we don't have to. We're not obliged to do that. So that's why we call them coordinates. It's something that we make up, right? It's like if you take this coordinate system, this point will have coordinates x, y, and z. If you pick some different coordinate system elsewhere, the same point in space, right? The same physical point will have different coordinates. And you can calculate what the coordinates are based on how the first coordinate system is related to the second coordinate system. Yeah. So I think, I assume that some of you took physics classes, right? So you probably heard of relativity theory by Einstein, right? So that's, he sort of capitalizes on the fact that the relativity means that everything is relative to each other, right? So it's when you pick a coordinates frame here and your sort of train or your bullet or whatever is moving there with some velocity. If you view this from a different coordinate system, this physical process looks completely different. And then, like, it seemed that the time slows down, etc. So this is all these things, they come from the artifact of the fact that coordinate system is not absolute. So it's our choice with variable we put on which axis. Good. So yeah, I mean, you can call them x, y, z. You can call them x1, x2, x3. But what matters is the order. So let me finish on that. So if this is x, y, and z, and now let me do something different. I'm gonna swap. I'm going to do my left hand, right? So it will be a different color: x prime, y prime, z prime. So you see, I swapped. I didn't change. Like in my picture, z still goes up, z is still vertical, but I swapped y and x. Equivalently, this could be done by if I just invert x. So if this is minus x, right, whatever that means, now this coordinate system and this one, they look the same, right? Because it's like flipping the direction of one of the vectors, one of the basis vectors, they're called basis vectors, so I'll get to that in a moment. When you flip it, you'll get from right triple, you get to left triple. So yeah, so she was asking, can we put z on the slanted axis? Well, then it's not called a Cartesian coordinate system, right? So, so later in class, we'll talk about coordinate systems where, although yeah, but I mean, in principle, you could do that. You could make it sort of like, you could make the z-axis to be, slanted, like it's not 90 degrees to the plane. But I mean, unless your geometry of your problem is really require that, I don't see any reason. So there's certain simplicity that comes with this 90-degree angles when you calculate the distances, for example. How is it still able to flip? You meant the same graph? Oh, well, just so like the black, so you have I drew in black x, y, and z, which corresponds to the choice of three vectors in the right hand, three fingers in the right hand. And now I sort of, I cannot do it with my hand, but think that you take your thumb and then you sort of put it in that direction. And then you call that thing the new x-axis. What I'm saying is that if you flip the x-axis and sort of you put it in a different direction, you will get a non-equivalent coordinate system. Due to the reasons that we'll maybe get into later when we'll calculate volumes. Yeah, that's right. Yes. You can put it this way. Okay. So how would you, let's talk about coordinates in a bit more detail. So let's say there's a point P suspended somewhere, well, somewhere in space, and it says it has coordinates x, y, and z. So what we're actually thinking here is that we need to, so that thing is, and then there's the origin of the coordinates, let's say O with coordinates 0, 0, 0. So you should think about it this way, that there is a, parallelepiped, with 90 degrees everywhere, so that one of its vertices is the origin, and the opposite vertex of that parallelepiped is P, right? So, the hell, probably is here. Well, I mean, okay, I'm just gonna draw it. I'm sure that it's no problem for you to imagine that. So like that. That's probably too long, not a bit of a stretch. Oops. Yeah, and then here, so if this point has P has coordinates x, y, and z, this point which lies in the xy axis has coordinates x, y, 0. This point which lies in the zy axis has coordinates, so x is equal to 0 here. right? It's 0 x and y, 0, excuse me, 0 y z. Now this point has coordinates. It's in the x z axis, so y is equal to 0. X 0 z. And then the remaining 3 points, they are as follows. This point lies on the z-axis, so it's 0, 0, z. This one lies on the x-axis, so it's x, 0, 0. And finally, this lies on the y-axis, so it's coordinate y, 0, 0. I'm using the notation a little bit, so like x, y, and z, that they're marking the arrows in the axis, and also notation of the coordinate, but I hope it's not going to be a problem. You can call ABC if you want to. You can find the coordinate. Okay. So some of you were talking about quadrants. Well, in two-dimensional Cartesian system, we have 4 quadrants. So in 3D space, we call them how many of them are there, and how shall we call them? Basically, what's the analog? Yeah, so it's 8. What's the name for each of them? Octants. Yes, that's right. Octa stands for 8. So, and the same way you can, of course, you have more choices, right? So if you 2 dimensions, you have so first quadrant is when both x and y are positive. Sort of same things happen here. Right? The first octant is where x, y, and z are positive, and then in most of the others, some of them will be positive, some of them will be negative. There is no point of trying to order them, right? Because it's kind of in 3 dimensions. Okay. So just to wrap up with this definition, so we call it the so each each of those lines, right? So see here these orange points, they all span the, so this x can be any real number, absolutely any real number without restrictions. Y can be any real number, and z can be any real number. So therefore, this x, y, and z, the triple of points, right? It's an object that lives in R cross R cross R, right? So the symbol is also called direct or Cartesian product. And you can multiply spaces. You can multiply vector spaces with Cartesian product, meaning that you just consider all possible sets x, y, and z, such x is in R, y is in R, z is in R. And then, of course, to shorten the notation, just say it's R in 3 on top. You don't say R cubed, you just say R3. Adjust the convention. So same way the 2-dimensional plane is R2. This is R3. Okay. Good. Now we already started talking about this. Let's talk a little bit about some simple subsets of R3. So maybe I should ask you this in form of question. Okay. So this is the definition. We'll see how you guys feel about it. So say we have this 3-dimensional system. And then I want to draw a plane which is parallel this question. In what scenario should we multiply each real number? So we'll talk about 2 different products which make sense in 3-dimensional system. One will be called the dot product. The other will be called cross product. Both products involve some sort of a multiplication. In fact, we'll have time, we'll get to that. Well, maybe not today, but early tomorrow. Right, so in a sense, it's really, maybe this notation may be a little bit confusing. So we actually call it the product of spaces, but what we actually mean is that you take you take all elements from first space, you take all elements from the second space, and you consider all possible pairs. That's what the product means. Yeah, it's there's logic to that name because, well, if R is one-dimensional space, each of those R's is one-dimensional. If you multiply them, you're going to get something three-dimensional. So in fact, the dimensions, they add up, right? As if they are some exponentials or something like that. But yeah, that's what product of spaces means. Good. So now, so you have a plane which is parallel to the xy plane. X, Y, Z, which intersects the z-axis at z equals 7. What do you think should be the equation that describes that plane? Z equals 7. Yeah, of course. Yeah, absolutely. Yeah, it's as easy as that, indeed. So it's literally, you should say this is Z equals 7. So it's Z equals 7, and this equation, this formula, does not depend at all on x and y, right? So in other words, for every value of x and y, right, every point in this plane will have the form x, y, 7, right? So you just you have a triple of x, y, and z. You just say, okay, the third guy is equal to 7 at all times. Okay. How about a plane that goes like this? So it's vertical. So it's now the plane is parallel to z-axis. In fact, it contains z-axis inside itself, and then it makes this black line belongs to the plane, and it makes 30 degrees. Radians, 5/6 radians with the y-axis. How would you describe this plane? So if you're in doubt, try to do the same with only in XY plane. So you have, what's the equation for this line here? In 2 dimensions, right? So there's x, y, and say this angle is pi/6. Mm-hmm. Is it √3? Why is it √3? So it's the oh yeah, is it? Oh right, it's the tangent of tangent of pi/3. That's right. Okay. So indeed so this angle is pi/3, right? And then we just say that here, okay. So y is equal to tangent pi/3, which is indeed x. So yeah, I think M will go off by the that way. So tangent is Oh no, no, I think you're right. No, yes, tangent is sine over cos. Yes, tangent is sine over cosine. Right. So sine of root pi over 3 is yes. I think it's root 3x. Do you agree? Yeah. Yeah. I put pi over 6 to it. Okay. So the equation of this line is y equals root 3x. What then what then the equation of this plane, of the purple plane, will be? So remember, it has to hold at every value of z. What's the simplest way to make it work? Yeah, absolutely, it's the same, right? So we would just say it's, yeah, absolutely. So y equals root 3x. It's the same. It's the same equation. Yeah. So again, so every point here, let's describe it. So now, so if y is equal to root 3z, so every point belonging to this plane will be described with x, comma, root 3x, comma, z, for any value of x and z. Right. So, and then of course you can do any, I think we'll do it a bit later in class, but pretty much any plane that looks like, which is oriented by any angle. Well, yeah, I'm not going to be able to draw a plane here, but any plane that sort of, well, does something like that, right? And it doesn't have to pass through the origin, can be described by an equation of degree of degree 1. So any plane in 3D can be described as ax plus by plus cz plus d is a constant, is equal to 0. Well, they're all constants. A, B, C, and D are some coefficients. And so it's a linear equation. It's a linear equation of 3 variables. Question from Sharon. I'm unsure what you did at the top right with square root 3. So when you have a line that goes like this, right? So its equation is y equals tangent of this orange angle times x, right? What's tangent of 60 degrees, right? It's sine 60 divided by cosine 60. So it's root 3 over 2 divided by 1/2. Yeah, good. Okay, yeah, so that's that. Now let's talk about distances, measuring distances. So in 2 dimensions, we talk about the formula. When you have 2 points on the plane, then you measure the coordinates, and then you sum the square of the differences of x coordinate and of the y coordinate. The same formula exists. A similar formula exists in 3 dimensions. Only now you need to add into consideration the z coordinate. So if you have this segment here OP, right? So then you can, the formula reads as follows: that OP squared is equal to x squared plus y squared plus z squared. Right. So the square of the diagonal of the parallelepiped is sum of squares of its sides. Right. To prove it, I mean, it's not really much of the proof. You just need to use the Pythagorean theorem twice, right? So let's do it like this. So this bottom, let's call this point maybe A. So OA, yeah, so this is the formula. I'll write it in a different way in a second. So OA squared is equal to, well, A has coordinates x and y, so it's x squared plus y squared, right? And then AP squared is equal to z squared. So now you use the theorem, which which is more than 2,000 years old. It's probably what, 2,500 years old, or something like that. Then you get OP squared is equal to x squared plus y squared plus z squared. Now, because the distance is positive, you can easily take out the square root, and then you need to take the you need to put plus here when you do the square root to get that. So this is the distance. This is the length of that segment of the diagonal in a parallelepiped. Now, if now we have 2 points with a so you have point A with coordinates x1, y1, z1, and point B with coordinates x2, x2, y2, z2. Well, then you need to do the same. You need to sort of think of it as you want to measure the length of the segment AB. Then you need to kind of construct a parallelepiped so that A and B will be in its opposite vertices, and then use the formula, do the same formula as we did. So you'll get something like this, right? And then there's stuff on the back. Now here and then the formula will look like this, right? So that AB will be equal to square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And this is the distance formula. Okay. So let's see what kind of what applications this distance formula will have, right? So now let's consider an equation. X minus 5 squared plus y minus 7 squared plus z plus 10 squared is equal to 100. What do you think this equation represents? Which shape in 3 dimensions does it describe? Yeah, so G1, it's saying it's a sphere, but can be more specific. A sphere, where is it located and what is its radius? Yep, that's right. Indeed, so what this formula is saying is that for all values x, y, and z, the following relationship is true, meaning that the sum of squares, meaning that the square of the distance, so this is the distance squared from point 5, 7, and minus 10 to that set, to that space, is equal to 10 squared. So square of this distance is equal to 10 squared, which means that the distance is equal to 10. So it's a sphere of radius 10 centered at 5, 7, and minus 10. So yeah, you would draw it like something like this. It's sort of because it's three-dimensional. It centers here, and this is this point. And the radius is equal to 10. Let me not draw the coordinate system. So it's right. It's in the, what is it? It's in the first, the center is in the first quadrant, right? And then it's sort of below, right? It's in the octant, which is sort of the lower octant, below the first quadrant. Yeah. Question, how did we get the numbers from this equation? Well, let's look at the distance formula, right? So now plug into this formula, take the formula with the square root. Okay, you got it. Other questions? Right, and then of course there are some other applications. So I mean, you can, so yeah, so for we can write the formula for any radius for any point. So sphere of radius r centered at point x0, y0, z0 will be described by this equation, as x minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to r squared. So you can see it's a quadratic relation. Well, it's same is true for in 2 dimensions. It's also a quadratic relation. Okay, so how about which set of points is described by the following? So say x squared over a plus y squared over b plus z minus let's just do without the point, with the shift. Z squared over c squared squared is equal to 1, less or equal than 1. What do you think this is? Now there's an inequality, and then I altered the equation a little bit. But in a sense that is recognizable, right? So we should have an intuition from 2 dimensions of what it should be. Again, if you're in doubt, you can ask the same question for the ellipse. Or that's right. So so it's an oval or ellipse. If you have a 2-dimensional, you can live in 2 dimensions in it. So let's forget about z for a second. So we had to remember that this thing with a and b in 2 dimensions was described by equation x squared over a squared plus y squared over b squared is equal to 1, right? And then if you say that you put less or equal than 1, you would look at all points which are inside, right? Because if you change this 1 by something smaller, you would effectively sort of have an ellipse which is inside it, right? And then you would you look at all sets, all possible ellipses that are subset that are embedded into a bigger ellipse. Now this is a three-dimensional analog. We get the z equation, and then these parameters a, b, and c. They are squashing parameters, right? They tell you about how much you squash or expand this shape in x, y, and z direction. And so the shape is called ellipsoid. So it will be ellipsoid if you just have equals 1, but now it's the kind of, you can call it solid ellipsoid, right? So it's a field, it's a solid shape. Centered at the origin, right? It will look like, you know, I'm not sure what's your favorite fruit or vegetable. So say it's a melon, right? It's one of those, or like this, right? And it's filled, right? So it's okay. So it's A, B, C. Okay. Okay, so on this note, when it is equal to any real number that lies in R, it's a solid. No, when it's equal, it's a. Yeah, so solid means that it's filled, right? So inequality is the inequality. When you have an inequality, it's solid. Like here, when you have an inequality here, then it's the 2D thing, right? When it's equal, then it's just called an ellipsoid. It's a 2D shape. So ellipsoid is the surface of this thing. It's a surface of this melon. Good, good question, Cameron. What if good? So Karen is asking a good question. What if I place? How about if I flip the sign? So x squared over a plus y squared over b squared plus z squared over c squared greater or equal than 1. What's that? Yep, that's right. Everything else is shaded. So it's rather, it will be the entire 3D space except that thing, right? Except that shape. So then sort of the way to write the formula, it will be R3 minus, like this backslash, it's the set theoretical subtraction minus, well, this, so minus the set of points which are described by minus this. It's like it's an infinite thing, infinite subset of R3, where we cut out this open subset. Okay, so on this note, I think we should take a, what is this slanted line? Well, okay, it's a good question. So you have a line like that, right? Next to the R. Will it be next to the R? Is that orange line, is it good for you, or is it? I'm not sure what next to the R means. Okay. Yeah, okay. Yeah, thank you. It's like, I didn't understand that. So this is, it's the sort of set subtraction. So for example, if you have a set A, B, C, D, you do this backslash B, that will give you A, C, and D. You just remove that set, right? So And now this is what actually should look like. That's what it says, right? So you have R3, it's the entire space, everything, all points in 3 dimensions, except those points which lie inside the ellipse. Good. We'll talk about lines later, after we do the vectors. Okay, let's take a quick break, and then let's meet in several minutes. We'll continue, but we'll be talking about vectors. Okay, I'll see you in a moment. Okay, welcome back. Oops. I think my screen sharing got disabled. Our next story for today is vectors. Or vectors in 3 dimensions. Right, so before, well, of course, we talked a lot about, well, in geometry, about segments. Let's say you have a segment AB, right? So how would we characterize what AB is? Well, it's a piece of straight line, right, that connects points A and B. So say A can have coordinates X, Y, and Z. B can have coordinates, well, maybe say U, V, and W. And you can say a lot of things about this vector, right? So about this segment. So the it's a piece of straight line in 3 dimensions. We can calculate its distance, its length. That's the distance between A and B will be equal to square root of X minus U squared plus Y minus V squared plus Z minus W squared. And of course, the you can see from the formula that it's symmetric, right? So you can, it doesn't matter from where to where you measure the distance, it's always the same. So therefore, the way we call it segment AB or segment BA doesn't really matter. So the idea of the vector is that we want to make a direction. We want to have a segment with a direction. So say now we have, so this is the same situation. So you have A, B, which are the same points in 3 dimensions. Only now I put an arrow at the end of it, and I call it a vector AB, and I put an arrow above it. So now it's the same. So now it's the so that gives me a certain order in this object. So if I have a segment AB, what would happen if I just swap points A and B with each other? So I just take A and replace it with B and vice versa. So nothing would change, right? So I just called them AB for convenience, but I could have done otherwise. I could have called them XZ or any other notation. I could use, Greek alphabet or Hebrew or anything. So it wouldn't make any difference. However, with the vector, it does, right? So if you flip it, if you flip A and B, then the vector will change, right? So vector AB and vector BA are different. So these are different vectors. Right? So that's why we should call, we call here A the initial point. And point B we call terminal point. Or the tip. Or initial point, sometimes we call the tail. You're thinking of like an arrow, which you shoot from the actual arrow from the quiver. Now the the interesting thing about vectors is that so that may look quite innocent thing to do. However, let's see the following situation. So if you have a vector here, let's call it AB, and then there's another vector here, CD, such that these two vectors still lie on parallel lines, right? And their lengths are the same, right? So consider this such that the length, so length by length of the vector we define well, length of the corresponding segment, right? It doesn't really matter, as we just discussed, it doesn't really matter which direction or you count the distance because the formula is symmetric. And then say, so CD, length of the vector CD is equal to length of the segment CD, and they're equal to each other. So consider two vectors which are parallel to each other, which have the same length. Well, what should we do in this case? So the outcome is that sort of the idea is that we want to call these vectors, we want to identify them, right? So these vectors are equivalent. So if this is the case, if we have one vector here and another vector here, and they are parallel to each other, so you can parallel transport, you can move one vector to another, then we call these vectors equal. So if this is the case, then vectors AB and CD are equivalent. So if I was sort of really strict about it, I wouldn't call it vector yet. I would just call it a directed segment, but that's sort of a little bit on sort of overstretched. So if you want to make a definition of what a vector is, so think of AB and CD are these two different directed segments, right? So it's a segment with arrows, a segment with a direction, and we call a vector the set of all directed segments which are parallel to each other and have the same length. And so a vector is a set of all parallel directed segments which have the same length. Yeah, so it's like we are sort of modulo that equivalence. But yeah, you have in other words, we think of a vector that as a directed segment with given length, which does not have a fixed tail or fixed tip. So we are free to move it in 3 dimensions. And so right, so say you have all these vectors, if they have the same length, they should actually be understood as one vector. Yeah. Sometimes the term displacement vector is used sort of to designate it. It's actually, it shows you direction in space where you're displacing it, like where the vector points, where it points, but you can do it in any you can do it from any point. So say these are all the parallel vectors. You could pick a point here, and then you just draw the segment with the same length, which is parallel to all the other vectors. Okay. Any questions? Well, sometimes you may have, like, in some, usually in some physics applications, what may happen is that you have you are forced to study vectors which are sort of whose tails are bound to some trajectory, right? So you have, say, particle that is moving along the trajectory, and then like you study only those parallel vectors parallel to each other, but only such that its tails are located on the curve, right, on this trajectory. That happens too, but that implies that your vector is satisfies some additional condition. In this course, we won't be talking about those conditions. So for us, vector is the set of all possible directed segments which are parallel to each other. It may sound a little bit abstract, but if you think about it, there is not much else that you can do, right? So if you say, okay, your direction is there, right? But then you need to say where you start measuring that direction, right? So, and the choice of the point is actually up to you. Okay. Okay, good. Now let's see what we can do. How we can combine vectors, right? So vector addition. So say you have a vector, and here you'll see momentarily that the fact that vectors can be freely moved parallel to each other is a bonus, right? It allows us to define vector addition. So say you have this vector, and then sometimes it's convenient to denote a vector with just one small letter. So all these purple guys, you can denote it with U, with the vector. In textbooks, sometimes people don't put arrows on top of the vectors. They use the bold font, right? But doing it it's not so convenient to do it and when you write, right? So it's convention when you write vectors in bold font. It's a bold font quantity is usually it's a vector quantity. So I'm going to do arrows, right? So say there's a vector U, it's the same color, and vector V. And you want to define what it means to write U plus V. Well, here's the rule. So first you take the tail of the second vector and move it to the tip of the first vector. And you do so by a parallel transport. So if vector V was pointed there, right, we just draw a parallel line and then draw vector V. It should be longer. It's like this. Right, so this is the same vector. So you first do that, and then you draw a new vector whose tail coincides with tail of the first vector, and whose tip coincides with the end point with the tip of the second vector. So this is U plus V. Now you may ask, well, what about, we know that addition should be commutative. It doesn't matter which order we do this. What would happen if I add V plus U? Are you going to get the same? Well, let's see. So if this was vector V, right? Then we need to do the same exactly as I said, right? So take the line that is parallel to the one that contains vector U, like that. And then you draw the vector U here, and then do the same. So you connect the endpoints, and that will be again the same vector, U plus V. Right, so V plus U is equal to U plus V. Well, and then you can sort of, the proof of the simple fact would be you can just draw these two triangles together as a parallelogram, right? So we can bring them together. We can bring their tails together. So this is U and this is V. V is a bit longer. And then you just draw the parallelogram. And then the sum will be the diagonal in this parallelogram, U plus V. Of course, from the geometry of the parallelogram, it is clear that the addition does not depend on it. Okay. So this is addition. Second operation, which we define on the vector, is scalar multiplication. So it's exactly what it sounds like. Say you have a vector, we'll make it shorter. So you have a vector U, and now you want to question, in what case would we add the vectors by drawing a parallelogram? In any case, I mean, it's really up to you. So see, well, a triangle is a half of the parallelogram, right? So, so there are three pictures that you can draw, which lead to the same answer. You can do the first triangle. You could do the second triangle. You can do them. You could do the parallelogram. They all give the same answer. I guess it's up to you which one you like more. Yeah. So let's say there's a vector U, and now you want to draw a vector which is 3 times bigger. Well, you can just do that, right? So that's exactly what it sounds like. So you just triple its length, right? Or you can draw a vector which is 1/2 of that. So this is U. Then this will be 1/2 U. And so it's the vector which has the same direction, only its length is by that factor different with the length of the original vector, right? So another example, you can take, again, let's take vector U, but now let's multiply it by a negative number. So if you multiply it by a negative number, then the direction changes. So for example, this will be minus U. So it's a vector U multiplied by number -1. So you can make a rule that, so if you have, so let C be a real number and U is a vector, well, in R3, for example, but it doesn't really matter in which space, then you define CU to be a vector whose length is equal to C times absolute value of C, excuse me, absolute value of C times the length of U. And direction is determined by the sign. If C is bigger than 0, then CU has the same direction as U, and if C is less than 0, then CU has the opposite direction. Yeah. Well, did we miss something? Well, what happens if C is equal to 0? Then we get the 0 vector, right? So well, we have 0 times U. It's a 0 with a vector sign. We haven't defined it. We haven't really defined it yet, but to have a consistent algebraic structure, so we want to learn how to add vectors. So that we'll talk about subtraction in a second. Subtract them. There should be a 0. Like there's something that's an element in this structure, so that if you add it, you don't change anything. So a 0 vector like 0 with the vector sign is just a point, right? It's it has 0 length. Its direction, the choice of its direction is irrelevant, right? So same way as so remember when we talked about polar coordinates, the choice of the angle, the polar angle when you see to the origin is irrelevant, right? It's undefined. Same way the same is true with the direction of the 0 vector. Okay. So now, with that in mind, let's define vector subtraction. So that's exactly what this picture represents with U and minus U. So we define U minus V. Let's say U and V are two vectors. We define it as the sum of U and minus 1 multiplied by V. Let's draw a picture. So this is U. This is V. Right, so our rule says that we need to add minus V, right? So let's do it like this. We can still connect together tails as if you're doing the parallelogram, right? So we connect together the tails of U and V. Then vector minus V, according to our rule, will be the vector which points in opposite direction and has the same length. And now we need to draw a parallelogram based on U and negative V. So it would be like this. And this red vector here will be U minus V. Yeah, that's right. That's the subtraction. Or you can just work with a triangle, right? So so in other words, U minus V, what is it? Is a vector such that if you add it to V, you'll get U. Right, so because how can you understand what it is, right? So we have vector U, and then this is vector V. Yeah, let me do it here on this picture. So because the red vector can parallel transport it, it will also be here. So red is guy here. So this one is again U minus V. As you can see from this triangle on the right, that well, the way to think about it is that U minus V is such a vector that if you add, so V plus this red vector, you'll get u, right? Simply because if you do v plus u minus v is equal to u, right? You can just cancel it here. So in other words, yeah, let's do it again. So this would be the vector. So if you want some mnemonic rule, well, you can just yeah, you can do it like this. So you can, if it's u minus v, then if you bring them together, bring their tails together, and then this is the vector which will connect the tips, and it will point from the second vector to the first. But personally, I like just to draw it every time, like the parallelogram, and check that subtraction works. Okay. Great. So now we can add and subtract vectors together. And then, of course, you don't always have to draw pictures, right? So, for example, sometimes the answer is clear from the form. For example, what will be u minus 3u? You don't need to draw the picture to show that this is equal to negative 2u. Of course, when you do when vectors are parallel to each other, you are simply subtract. It's as if you have a point on the coordinate line, and you just subtracting its coordinates, right? Which brings us to the next point, to the coordinate presentation of vectors. So let's draw the coordinate system. And then let's draw a bunch of vectors. In fact, it will be the same kind of vector here. So because the endpoints of the vectors are not fixed in our understanding of how vectors works, Cameron is asking, by the way, that you had the vector subtraction, wouldn't they yield a minus u vector? Or does distribution of signs do not apply? Well, it does apply. I'm not quite sure. Okay, good. Yeah, you get confused about something. Okay, so because the direction is actually not fixed, we can just pick our favorite point, which of course in the coordinate system should be the origin, right? So well, pick a different color here, so that pick this distinguished point, where the tail of the vector is the origin. And then you can just ask yourself, what are the coordinates of the tip of the vector? Right, so if this point has coordinates x, y, and z, then we can just assign to the vector, to this vector, let's give it a name, so again, it's a vector u, assign to the vector u these three coordinates. So we just say that u is equal to the triple x, y, and z, right? So, well, and your book is using different notation. It uses the angular brackets, but I don't like them too much. So I'm just going to be using, using the same notation. So it's x, y, and z with the parentheses. And the reason for that is because so if you wish, then there is a one-to-one correspondence between points in the space and set of all vectors, right? So each point uniquely gives a vector, and otherwise. simply what you need to do, you need to bring the tail of the vector to the origin, and then the tip of the vector will be located at that point that you're interested in. So in other words, yeah, this triple has now a new meaning. Not only describes points in space, but it also describes coordinates of vectors in space. Of course, the parallel transport means that if you move this vector elsewhere, let's say here, right? So then, well, of course, the coordinates of the tail and of the tip of the vector will now be different, but the differences between those coordinates would still be x, y, and z, right? So, say this point has coordinates x0, y0, z0, and this point has coordinates x1, y1, z1. Well, then, well, guess what? So then x1 minus x0 is equal to x, y1 minus y0 is equal to y, z1. Okay, but this time my neighbors, yeah, they started 15 minutes before the end of the class. Z1 minus z0 is equal to z. Okay. Good. Yeah, and that also brings us to the formula that if you have 2 points, let's call them well, A and B, right? So if points A and B are given by these coordinates, then vector AB is described by coordinates x1 minus x0, y1 minus y0, z1 minus z0. And of course, the opposite vector BA is described by you just do the subtraction in different order. x0 minus x1, y0 minus y1, z0 minus z1. So yeah, so if you have coordinates of 2 points, then just subtract one from the other to find the coordinates of the vector. Okay. Okay. So now let's come back to our construction of addition and then scalar multiplication and subtraction, and describe this in terms of components. Right. So let's go back here. So if vector u in this new understanding had coordinates x, y, and z, and vector v has components u, v, and w. Yeah, need to do a better writing. U, v, and w. Then u plus v has coordinates x plus u, y plus v, and z plus w. Right? What you're simply doing is that you are adding x, y, and z components of those vectors, right? So let's see why this is the case. Let me draw here. So for simplicity, let me draw the 2-dimensional plane, right? It will be just easier to trace what's going on. So say this is the y-axis and this is the x-axis. Actually, I think we should have put them in the origin of the coordinate plane. Yeah. So okay, let me just make a new picture. See, U was in black. right? Then yeah, we need to do the parallelogram. Actually, for this particular matter, the triangle is better, but anyway, let's do the both. So it's u plus v, and then yeah. So by our construction, by our definition, this endpoint has coordinates. So this is v, right? So it has. I just found out I've used the notation. I denote coordinate with the vector and the coordinate with the same letter. Okay. Okay, let me quickly relabel them here just for this picture, but I hope it won't be confusing. So let's say u has x1, y1, and then v is x2, y2. It's for this particular illustration. So because v has coordinates x2, y2, then this coordinate is x2, right? And this coordinate here, endpoint of u, right? It will be rather this distance here will be equal to x1, right? Because x1 is the projection of this vector. Sort of, it's the so u here. It's like this, right? So this is x1, and now, well, this segment here is equal to that one. So therefore, this endpoint has coordinate x1 plus x2. And you just add in the x coordinate and y coordinate of the vector, and if you live in 3 dimensions, you get an x coordinate, y coordinate, and z coordinate. Okay. So to summarize, addition of vectors implies addition of their coordinates. As simple as that. Analogously, the scalar multiplication of the vector, let's say again, say u is equal to x and y. Now c times u simply has coordinates c times x, c times y. So scalar multiplication of coordinates, excuse me, scalar multiplication of the vector amounts to scalar multiplication of its coordinates. Right, so you change each of the coordinates by the same factor. And finally, vector subtraction works the same way. If u is equal to x1, y1, v is equal to x2, y2, then u minus v has coordinates x1 minus x2 and y1 minus y2. So as we'll see later this week, the coordinate method is really convenient to do calculations with vectors. You just put in the numbers without even thinking about it. Okay. So as a summary for this topic, let's list the properties of vectors. So number one, it's the addition is commutative. So a plus b is equal to b plus a. This is so-called commutativity of vector addition. Next is that there is a zero vector, so that if you take a plus 0, you get a again. then if you do the scalar multiplication by number c to the sum, right? So then you can do it in a different order, right? So you can do it's equal to CA plus CB. This is called it's the distribution law. Okay, then of course there's a distribution law relative to the multiplication of scalars. Right, so it says scalar. If you haven't heard the term before, a scalar is just it's not a vector. It's a number. So it's something that doesn't have a direction. Yeah, it's like when you talk about some vector quantities, then scalar means that it's just a number. And so it's the same as multiply C, multiply A by D, and then multiply by C. Finally, there's a distribution for addition of vectors. It doesn't matter in which order you do the addition. So yeah, so it's so this is called associativity law. It's not associativity for addition. Then A plus minus A is equal to 0. And then C plus D times A is equal to CA plus DA. And finally, there's a multiplication. If you take 1, you multiply. So out of all scalars by which you can multiply, there's 1. So if you multiply it by 1, it doesn't change the vector. So this is a commutativity. There's a word here. Commutativity. It's a property of the which says that it doesn't matter which order you do the operation. So addition is commutative. Okay, yeah. So this is the these are all properties of vectors that we need. Yeah. So this algebraic structure is also called the module. One is, but actually, so that's what it says, right? You have your objects. You can add them. Addition is commutative. There's a 0 in addition, so it forms a group with vector addition. And then you multiply vectors by numbers, right? And these properties are satisfied. Okay, yeah, and I think right. So I think probably the last thing I want to add for today is that we can in the coordinate system, it's convenient to assign coordinates to the x, y, and z vectors, right? So there's a vector of unit length that is, we can call it vector I, which has coordinates 1, 0, 0. So it's a vector with the length equals to 1 that is directed along the x-axis. Then there's a vector j, which has coordinates 0, 1, 0. And then vector k, which has coordinates 0, 0, 1. And so we can write them again. So I is 1, 0, 0. J is equal to 0, 1, 0. And k is equal to 0, 0, 1. And this is convenient because every vector in 3 dimensions, let's say I, you can write it as x I plus bj plus ck. Excuse me, not y, not xy. Let's do say if vector A has coordinates x, y, and z. If vector A is like this, then we can also say that it's represented as the sum of unit vectors that are directed in x, y, and z direction, right? So here, if you calculate the length of vector I, you'll get 1. Length of vector j, you'll get 1, and length of vector k, you get 1. So you can check that these two forms of vectors are equivalent to each other. So you can either specify its coordinates, or you can say that the vector is obtained by a sum of the following things. You take the vector of length 1 in the direction in x direction, multiply it by the x coordinate, then do the same in y direction, and do the same in the z direction. And that will you'll get to the same point, right? So let's do it one more time. Say this is the vector A, and if you draw the parallelepiped, as we did, then this vector is I times x. This vector is j times y, and this vector is k times z. So A is xi plus yj plus zk. So ijk are also called coordinate vectors. And because they give you the coordinates of a point or a vector, and the fact that they have their length is equal to 1, we call them vectors of unit length. Right? It's unit means that it's these three conditions are satisfied. Okay, good. I think that will be enough for today. So the homework is out. You're welcome to practice, to start practicing. And I'll see you guys tomorrow. Okay, thank you.